This is it, the last video for the chapter 4 in the DB2 lecture series. And well, yeah, it's time to switch over again, to switch from PostgreSQL to MonetDB. So this is the game now. We are switching from the disk-based system to the main memory-based system to see how MonetDB reacts if we perform queries that access some columns, but not all of them. Some columns are being projected away. And of course, to have a comparable situation, we will query the table ternary again, the ternary ABC 3-column table. And we will, of course, perform the same query on that table. It's the probe query Q3. You see it here. You've seen it many times already. We are scanning all rows from ternary, but we are projecting some columns away. You see that the B column is not being included in the result here. And this makes all the difference between the PostgreSQL and the MonetDB systems. As you recall, MonetDB is a column-oriented database system. We have different butts, different column vectors prepared to store the contents of the A, B, and C columns. These are separate vectors. Okay, so now that we see that the B column is not relevant to produce the result for this query, we expect the system to not even touch the B but the B column vector, and really save some effort here, save some memory movement effort, and save some CPU effort to not produce the B column. This is actually where the column-oriented DBMSs shine. Selectively access only those column vectors, in the case of MonetDB, the participating butts only, to produce the final answer of the query. Okay, so let's provide the necessary playground here for our talking to MonetDB. Let's first see whether there is a MonetDB shell running. It is a SQL version of the MonetDB shell. The M client is running, and we're talking SQL to MonetDB to create the ternary table. Send the DDL, send the DML, so insert the 1000 rows into the 3-column table. Okay, that's it. And then perform query Q3, of course, using the DBMX X-ray, the explain command. And as you see, we are not accessing column B. It's being projected away, and we expect the system to not touch the B but or B column vector at all. Let's do that. All right, mark the query, evaluate. There you go. The plan or the timing information, but the mul statements are here in front. Okay. So this is the plan. This is the initialization of the SQL subsystem. This is the access to the row visibility information, as always. And then the individual column vectors, the individual butts of the relevant columns are being accessed here. And as you can see, there's only 2 of them. There's the C butt, or the butt for column C is being accessed. That's the butt of doubles. And the A butt is accessed. That's the butt of integers and nothing else. There is no mention of the B butt here. The B column vector remains completely untouched. It's not needed. It will never be brought in from secondary storage. No single bit of memory is wasted on that. Okay, then some preparations for the construction of the overall result, which is then found using this SQL result set mul function that we've already discussed. And that's about it. No mention of column B at all, as expected. That's where the column-oriented DBMSs really shine. Really selective access on the needed columns only. All right. This is an excerpt of the mul program, the mul plan that you've just seen in the interactive editor. And as you can see, we are only accessing the C and the A butts here. That's as we expected it. What we also see is once these column butts, these column vectors have been accessed, we of course perform the algebra projection operations to apply visibility information. But of course, only 2 of these algebra projection operations are needed. because only 2 result columns make up the final answer to this query. And only these projected columns go inside the SQL result set function that will construct the 2-column result for us. So to really bring that point home, let's look at the situation in graphical form. So on the left of this dashed line, you see the PostgreSQL situation. So one page of PostgreSQL information in abstracted form. This would be one 8 kilobyte block organized in the row-based fashion that is so typical for PostgreSQL. So PostgreSQL is following the n-ary storage model. Rows are being held together in contiguous memory. So one particular row would be this row, and it would be one row of our ternary table. Some bytes are invested in storing the A values. Contiguous bytes immediately adjacent would be invested in storing the B column values, the textual MD5 hash, and some bytes would be invested in storing the 8-byte float here, so just represented by these 2 C's. But the B column is being projected away, so actually the largest part of the row that I'm highlighting here would be brought in from disk, would have to be scanned by the CPU, but would have to be ignored. It would have to be completely ignored. So the actual useful bits that are brought in from disk, the useful bits for query Q3 are the shaded one, the A part and the C part. Everything in between here is unneeded and has been brought in vain. So next row, only the A and the C part, only the A and the C part, and so on and so on. These are the only relevant bits to the construction of the result for Q3, and the lion's share of this page has been brought in from disk and has occupied space in memory without contributing valid or useful bits to the answering of query Q3. All right, it's different on the right-hand side of this dashed line, where we enter the column-based world of MonetDB, or the decomposed storage model, the DSM model. We only access the relevant columns, only the A and the C columns. You see no mention of the B column vector here. It's not being accessed at all. All the bits that we are scanning here from top to bottom in the A and the C columns are really relevant. So only these shaded parts here in these A and C columns, nothing irrelevant has been brought in. The CPU will scan over this piece of memory and will only find relevant bits that are used in actually answering the query Q3. 100% of the data loaded is really relevant. All right, and as you can imagine, the brought-in column vectors, the A and C vectors in this case, they not only occupy space in memory, they will also occupy space in caches, in the CPU caches. There is really limited space there, and anything that we don't have to bring in the CPU cache will not lead to the eviction of maybe other relevant data. And that's a good thing. So the less data we touch and the less data we bring close to the CPU into memory and then also into different cache levels is a win for us. And that's exactly what happens when we look at the DSM model and MonetDB's approach. So even for such a simple query as Q3, a quite fundamental difference between the PostgreSQL, the NSM, and the MonetDB, the DSM worlds. All right. So that would be to draw a line under the chapter 4 of the DB2 lecture. There's more interesting stuff coming up. The probe queries will get more complicated and more interesting, and the internals relevant to processing these queries inside PostgreSQL and as well in MonetDB will become more interesting as well. And I cannot wait to share that with you. So please stay tuned. Take care and see you soon. Bye bye.